Welcome, everybody. We're very excited to have you join us for this Safety in the Loop live stream. We are super excited to have these very special guests with us today, and we're very excited to have you join us today. So feel free to drop your questions, your comments at any point through the live stream. We're going to take different points throughout. I'll cover general news that don't impact the topic we're talking today at the end of the live stream. So don't leave when we finish the discussion. Hang up for a few more minutes and go over some quick news I have from the team. But today, we're going to teach how NVIDIA's Halo outside-in safety AI agents improve robotic safety with contextual awareness and protection through infrastructure-mounted cameras. It's going to be very exciting. If you're watching this, which you are, you're going to learn why outside-in safety is important for AI-based robots in warehouse, industrial, and logistics industries. You're going to learn about key features in NVIDIA Halos outside-in safety AI agents, use cases safety AI agents can support, and how to build applications easily, and how NVIDIA Halos can improve your overall safety measurement. To help with today's topic, we have some very special guests, which we'll introduce right now. Next to me, you see my great colleague, Riccardo. Hey, Riccardo.
Yeah, hi everyone. Very happy to be here again. And so, my role at NVIDIA is to work on industry safety and also helping AI and safety be friends all together.
Very important indeed. Very happy to have you here. We have another colleague from our team, Suhas. Suhas, thank you for joining.
Hey everyone, I'm so excited to be here. About my role, I lead the product management software side on the Edge and Robotics group. And so excited to be with folks like Riccardo and Bodo, who lives and breathes safety every day. So looking forward for it.
I agree. I've had such a good time in these warm-ups and really blown away by the information that everyone's going to see in a few minutes. Leading to my next guest, Bodo, so happy to have you join us here.
Yeah, thanks, folks. Really glad to be here. Thanks for having me. My role is I'm helping Riccardo and NVIDIA to make sure that the safety solutions here are actually certified by accredited bodies like TÜV Rheinland here in this case.
Well, okay. This is great. So as everybody can tell, we're going to have a great discussion over the next hour. Again, reminder to post your questions and comments. Let us know where you're watching from. That's always interesting for us to see. But let's dive right into it. Let's talk first about robotic safety and what some of the challenges are before we dive into actually how to deal with this. And I think to help kick that off, we have our colleague Suhas is going to run us through some slides, I think.
Yeah. So Edmar, can you share the screen?
Here you go.
Yeah, thank you. So before we start actually asking Riccardo and Bodo about like their views on different aspects of AI and safety, I want to kind of set the stage and show you how we what happened. Where's my next slide going? Just a second.
That's okay. Take your time. And we see some great comments coming in already. So thank you everybody for tuning in. We're broadcasting today to our NVIDIA Drive LinkedIn page and the Omniverse YouTube page, as well as X. So absolutely feel free. Suhas, I think you need to start sharing your slides one more time and I'll be able to see it.
One more time. Okay, just a second.
We'll also be sharing a dedicated Discord thread for this live stream. So if you're watching this live or after the fact, you can leverage that Discord thread for asking your questions afterwards. And I think I see your slides right now. I'm going to share them. Here we go.
And you're able to see my slide going to the next one too?
Yes, correct.
Okay, perfect. Now we are set. So before we start talking to Riccardo and Bodo, I wanted to kind of set the stage of how we look at safety. We look at safety and define safety in kind of three different buckets. One is what is reactive safety. Reactive safety is where this traditional safety mechanisms today built into the robot, where the safety is handled once the safety situation happens. So it's kind of reactive in nature. The second bucket is proactive safety, where you identify the safety concerns before you perceive the safety concerns before it would happen and take safety precautions. Third is predictive safety, where even before you commission the robot, you're predicting what kind of safety situations that might happen when it is commissioned, and simulating it in the simulation and testing out your safety concepts. So in our definition, we look at safety in reactive, proactive, and predictive. Now, there are some challenges today with traditional robotic safety. One is blind spots. The safety sensors which are used, depending upon where the robot is positioning and where the pose of the robot and the direction of the robot, these safety sensors might have blind spots where it cannot see. Or it might be occlusions, which might be a problem, where the sensors are not able to see through. For example, it could be a wall, or it could be an aisle in the warehouse, which it's not able to see through. Or it could be a temporary obstacle which is blocking the safety sensor. And blind spots and occlusions are one of the common challenges with respect to robotic safety. What does that mean is it limits the perception capability of the sensors which are connected to the robot. Second is the today's safety is more or less reactive in nature. So it will respond after a safety situation happens, not proactive. And we went through what do I mean by reactive and proactive in our previous definition slide. Also, what's happening is because of the safety concerns, the robots are artificially being slowed down. And because of that, the overall productivity that the robots can do is actually also lower. The same safety concern is also restricting how humans and a robot can interact with each other seamlessly. So, because of that, the seamless collaboration of human and robots in shared space is not happening to the full extent it could happen. These challenges are actually are some challenges that can be solved, and that unlocks the opportunities that can happen with functional safety. How do we provide 360-degree situational awareness, eliminate blind spots, and deal with occlusions? How do we make safety incidents perception more proactive in nature rather than reactive? How can we boost productivity by not slowing down the robot artificially? How can we increase the human robot interaction? And at the last, how can we do all these things while being compliant to functional safety standards? So these are some of the opportunities which are still to be unlocked with functional safety. And we believe AI is the answer. And this is where I will turn to Riccardo and ask him to talk about AI's role in safety.
Yes, many thanks, Suhas. And in fact, I want to start a bit with an history, also to also focus on the challenges. So, if we look more back to the adoption of AI in systems, we had a first wave in which very simple AI like CNN was used for tasks that they were no or very little implication for safety. For example, if you think to a robot on a warehouse, you detect object, maybe for maintenance, or it's like a bottle or an equipment. Then in a second wave, we started using more advanced model like DNN and so forth to do tasks with safety implication. For example, again, in a warehouse, as we will see later, robot, you need to detect a human to avoid a contact or slow down the machine. Now we are even on a third wave, in fact, or even a fourth wave if we want to think like that. So now in which we use foundational model, reasoning VLA, in order that we give to the model a behavior that is really human-like on and also so related to safety systems. So that is the key point. And also the other point that I want to emphasize is also the impact of AI on the different layer of a physical AI system. Of course, one piece is the impact in the safety of the hardware and the software itself in the platform. So just to give you an example, you need a compute, a very powerful one, to execute AI in this field, and then you need a software infrastructure, you need also software around that. And then on top, you have the safety of the algorithms, in which you have all the different aspects. And I think later we will show how critical it is to achieve safety in each of those elements, like the MLOps, the role of the validation, the data set, and so forth.
So Riccardo, when you say physical AI, I want you for this audience to actually first define what physical AI mean, so that we are all on the same page. And secondly, how do you define safety in physical AI systems?
Okay, so that's It's a great question. So, and in fact, it's also important because when we define safety, safety may have so many different aspects. So, what we are somehow the focus of the discussion is AI that is also doing action in a physical world. So, interacting with human, interacting with machines, interacting with a set of assets. And how we consider safety in such a context. I mean, in general, safety, you always start defining the product that you want to achieve. And in parallel, and this I think we will see with Bodo in a second, all the regulation and standards that you need to fulfill. Then, on that basis, we perform, anyway, this is always true in safety, a risk analysis. And this involves identifying all the potential hazards, everything that may be wrong. And then we somehow identify and we correlate with exposure. So, how likely that event may happen, the severity, how bad the outcome can be, as also the role of humans, that for an AV could be a driver, in case of a robot could be the supervisor, in order to help the system on being safe. So one of the key things on system using AI is, of course, the analysis of AI failures. On that, on the basis of the analysis of AI failure, then you derive a list of requirements, let's say the physical AI safety requirement, and then and it's a complex job that requires a lot of effort in the sense of also understanding what you do at the architecture level, what you do at runtime level, and what you do at the validation level. What you do, you define a set of guardrails. And guardrails is really the essence of how you make AI safe.
So, Bodo, here I turn to you, and kind of you have been in this safety standards from a very long time. So, I would like to get your views on what's the role of safety standards in physical AI safety.
Yeah, and again, that's a good question, and I mean, I think Riccardo already started to explain this really well. I mean, in the end, it all really boils down to best practices, what people have learned, and the basic paradigm for functional safety is really the absence of unreasonable risk. So I mean, so we really won't be able to say a system is free of risk, then since as humans we haven't been able and learned how to do that yet. But society basically tells us that in the end we need to make sure that whatever we build needs to be safe enough that as society we can tolerate these certain risks, and so that's what it boils down. And then this diagram here is kind of nice because it shows all these standards, and then we are starting at the bottom with generic safety standards. The most important one, at least in my humble opinion, is IEC 61508. I mean, that standard's been around for more than 20 years now. And it basically has been teaching us how to deal with electric and electronic systems, and then making sure that any failures in there cannot really create an unreasonable risk. And now, since these standards have been, the standard has been around for a while, it's very generic. It's also not necessarily the easiest one to wrap your head around and then use, specifically if you're in a certain industry. And for that reason, a lot of industries have said, well, we need something that's more tailored for our industry. So the automotive industry went in and then got a safety standard, which is ISO 26262. Riccardo already said it. I mean, it's always severity and exposure is always something that all standards have. This standard also adds controllability, so humans can really affect something potentially, and then that really impacts on how you classify your risk. And there are other standards out there for railroad, for aeronautics and so on. But since today we are talking industry. I'll focus a little bit more on the industry standard. So you'll see this as further up we go in this diagram. Then, for example, we see safety sensor standards out there. Then we have machine cell building standards. We have autonomous robot standards when they're moving around. And then finally, we have collaborative robot standards. So basically now we are starting to really have robots that interact with humans while they're performing certain tasks. And I mean, industrial robots, again, have been around for, well, more than 30 years, but these are machines that can weigh hundreds of pounds. They can move very quickly. And if a human stands next to them without any safety mechanism, some very bad things can happen. That's the reason that robots traditionally have been in cages, but now with collaborative robots and so on, we are actually moving in environments where humans can stand next to a robot, and we still, with our mechanisms here, we make sure that, well, no unreasonable risk is going to occur. And then, so that's going to be our introduction. And then, so we'll be talking about AI and functional safety standards, yeah, in the next slide here. So, I also wanted to give you guys this overview here. Sounds intimidating, but maybe it's not, since the left side here, this is why it's in friendly NVIDIA green. These are the things that are out there. And in my mind, there's a very good framework out there already. I mean, so anybody that's interested right now and then really wants to purchase a standard document can for sure work with ISO TR 5469. This is a TR, so this is a technical report. So that means it doesn't include any requirements that I, as working for a company that's doing testing, inspection, and certification, I can't really write you an inspection certificate against the standard because it only has requirements. But still, this standard really is a great summary about what you need to think about when you're doing AI and functional safety. And it was developed by the standard committees that you see here on the slides. I'm not going to read them all for you, but it should really be mentioned that Riccardo here was really intimately involved in that standard. And then I think a lot of the experience from that is going into the standard that's 2 down, the ISO IEC 22440 series of standards that's getting pretty close to get released as a draft. This now is really a development where the technical report is being moved into a TS, a technical standard. So this document will have requirements that really say you shall do this. And then I could come in and then basically take my magnifying glass out and say, well, have you really done this? And if so, then I'll give you a letter saying, yep, you've done that. And then you can basically prove to other people, yep, you're following that. So this is a really important next step. And then also, since we were talking automotive, ISO Pass 8800, this came out last year, so in December, so it's not quite a year old yet. But now for road vehicles, we have an AI safety standard that's applicable right now. So if you an automotive tier 1 or OEM, then that one is applicable for you now, so you have to follow that. And then another one that's in the pipeline is ISO TS 25223, and then that's basically talking about uncertainty evaluation and quantification. So I mean, another super important topic for AI, because one of the things we should be saying here, I mean, our world's changing. When I started doing functional safety many moons ago, software was basically the only thing you had to worry about. The software were systematic faults, but well, now with AI, software also has random faults that we need to address in a certain way. And then to the right, and I won't read them all to you. I mean, these are some auxiliary standards. Some of them are also technical technical reports, so they're just guidelines, but some of them are good to read, and then at least one of them, I won't tell you which one, let's see who finds out. So some of them will actually be showing up later in this presentation when we're talking about life cycles and so on. But in any case, I mean, if you're working in AI, you want to follow international best practices and standards, then this might be a good reading list.
Yeah, and I saw a question, Bodo, that I think it's interesting in this framework that is about, there is a standard now on humanoids. In fact, that is the ISO 25705-1 that just we started. I think it was in June. And is a good example because that standard that is currently building is already, he's discussing about having the link with the ISO ICTS 22440. So in this way, those standards are starting to refer to using AI in that context.
Yep, great comment, thanks. And so, and yeah, and then we also should be talking about AI lifecycle and verification and validation. So again, if you maybe wait another half year or so, and then ISO TS 22440 is going to be out and then going to be valid for robots, and then you will have to follow that if you bring a robot out, and then you want to show that that robot, that industrial robot, is functionally safe. Then it's important to understand that we are not really starting a revolution in these standards. So what you see in the top left thing is something that was around when I went to college, and like I said, a couple of moons ago. So a V model, and please don't think we are all still doing waterfall. I mean, this paradigm is valid if you're doing agile, Scrum, or whatever other techniques you're doing to develop. This is just simply to show how our verification and validation works. And I mean, the idea is really you go from the generic to the specific. So the top left is very generic, and then the bottom is very specific. And then the other thing is when you basically horizontally, you'll always have to show that for something that you specify on the left-hand side, there is some sort of test case, some verification, validation around there that then in the end proves that this specification that you created actually has been implemented. And then again, from the vertical traceability, requirements shouldn't really exist in a vacuum. So I mean, you go from the generic to the specific, and then that's basically shown with the vertical traceability here. So that's still the approach. And then if we're looking at the right-hand side here, that basically gives you your typical model for a development cycle. So you basically start on the top with the inception. So that's your idea. You're talking to your customers. You want to put something together, and then you'll see some of the steps in here. I mean, maybe the key one is really you should talk to your stakeholders and find out what they want. Otherwise, you might be building something, but you might not be able to sell it. And then in the next thing, the next stage is the design and development phase. And so also really classical requirements first, architecture next. So if you flip this around, then it will be interesting to see how you can consistently do this. But so that's usually the idea. And then obviously now going up on the right-hand side of the V, we are looking at verification and validation. And then in the end, since we are talking life cycles here, so I mean, a life cycle goes beyond development. It goes into actual deployment. When you have your product out in the field, you need to service it, you need to maintain it, you need to repair it. And then in the end, every time everybody has a right for retirement. So your product eventually will be sundowned and then enjoying something with an umbrella, drink with an umbrella on the beach. So when that happens, the retirement is another step that needs to be planned, and especially if you're cybersecurity, well, if your product retires with some secrets, that might not be these are good. So that's another part of the life cycle. And then here you can also see that we have re-evaluation on the left-hand side here. So when we see something during operation, I mean, and that's something that all safety standards do, then you probably won't be catching everything during development, as I mean, regardless on how rigorous you are. So, but if you do catch something, then you basically have to reevaluate your product, and you might have to then put something else in there to address safety issues that you found in the field. And then obviously you also do continuous validation in the field as well. And to the left, I just gave you another thing that nicely dovetails into the three phases that AI often has. I mean, you have a training phase, you have an evaluation phase, and then you have a utilization phase where you're actually working with your product. And then this diagram shows you then how this works. Obviously, in the training phase, you use raw data and you make a training data set out of it. And then you have your implementation process. And then out of that, hopefully you get your trained model. That then goes into the evaluation phase. So here you have your test data set that's hopefully representative and selected as per all these criteria that these standards that we mentioned a few minutes ago really spell out. And then out of that, you get your test results for the trained model. And then if the test results basically satisfy the key performance indicators you've set up before, or my friend Phil Koopman would call them safety performance indicators. But anyway, so if you're satisfied that everything works, well, then you can actually bring your system out there in the field and then operate it.
Hey, thanks, Bodo. Thanks for kind of going through and explaining the AI life cycle and the processes that need to be in place. I'll go back to Riccardo. Riccardo, for a AI-based safety, there are a lot of things need to happen at each and every layer. You need to think about the processes at the hardware level when you're designing it, the software, the AI architecture, the algorithmic architecture, and such. What is NVIDIA doing in this regard? If you can explain the strategy of NVIDIA.
Yes, and I think exactly what has been shown by Bodo is also so focusing on the need of addressing these really end-to-end. So what we are doing is what we call Halos. Halos is a full stack system that we have started with autonomous vehicle and now extending to robotics, as I will show you in a second, that cover, as you have said, basically everything starting from the bottom. So the way you develop your software and your hardware according to the safety standard that have been shown by Bodo, then the way you have your SoC, and we will go there, I think, in a second on IGX, that includes, I've seen some of the question, of course, you also need to identify failures in the hardware, failure in the software, and generate alarms that then they are used by the component of the system to fail over. That is also starting at that level. Then there is the overall system, the board, the component, the power supply, and so forth. But then we have all the AI aspects, so the algorithmic safety, and we will see in a second this outside-in agent, how is architected, the safe MLOps, that include also, that was another question, interesting one, so that safety is not just, let's say, or avoiding or detecting something from happening at first, but also it may happen, as Bodo said. So you need to have a flow that essentially learn out of this and improve. So during training and during verification and validation. And then at the end, you have the all the infrastructure that you need to have when you deploy into the field, and then up to the AI system inspection lab, so helping our customer. Though this is Halos in general. And I think if we go to the next page is how what are the pillar of Halos in robotics. So basically those are the 5 elements. First, the safety platform, the hardware and software. And I think, Suhas, you will go through it in a second. Then we using a platform like that is able to reach certain level of safety, then you can either implement inside out and outside in. And again, I saw a question if Halos does outside in only. No, Halos is, I mean, is everything. So the platform can be used for inside out safety. So basically using sensor on board, and the outside-in agent that is the topic of today. But the platform, the foundation of the platform, of course, is used to address all of those. Then there is an important aspect that we will cover in a future live stream. We have already seen for AV, and we will cover in the future for robotics as well, is that the use of basically the simulation tool either during the flow when you develop an AI system, but also used as in a predictive way. And then finally, the AI system inspection lab to help our customer to get ready for the final assessment and certification by certification agencies.
Perfect. So with these 5 pillars, starting from the platform, then the inside and outside, and the 2 ways of looking at safety, simulation, and then the inspection lab. I'll zoom into the first pillar, which is the safety platform, and we'll go to the outside and safety in a bit. So IGX is the platform from NVIDIA who brings for robotic safety, who brings 2 things: AI, a powerful AI compute, but also safety in one single platform. So IGX Thor that we announced a couple of weeks back provides up to 2070 FP4 flops, almost like 2 petaflops of performance right at the edge. It has 14 Neoverse ARM CPU cores. It has 128 GB memory with 273 Gbps memory bandwidth. That is more than sufficient for you to run a VLAs, a big VLAs, VLMs, LLMs. So it's meant for like this foundational models. Of course, it is industrial grade. The hardware is not only built for AI, but is also built for safety. And what do I mean by that? Is that it is rated for SIL 3 IC 61508 for systematic failures. It's rated for SIL 2 for hardware random failures. It includes inside the SoC itself a functional safety island. It's a safety island which has 4 lockstep ARM R52 cores where you can run your safety concepts. There is also hardware safety extensions built into the SoC itself, which includes doing ECC, doing parity, doing illegal address detection, also doing bus monitoring for any errors. And also there's error detection, collection, and reporting to functional safety island built into the SoC. It has in-system test, so which tests various IPs during boot up and can make sure that your system is booting up into a safe state or an unsafe state. If it's booting up to unsafe state, then we do the reporting to the functional safety island or a safety MCU that you can bring in your designs in your carrier board. Measures for freedom for inference is also part of the hardware itself. Now, what we do is, on top of that hardware, we enable these safety features through a software package, what we call it as safety extension package. So this package, when installed, it enables these safety features, including collection and dispatching of the hardware errors to FSI and safety MCU. We provide reference firmware on both the functional safety island, which is inside the SoC, and also safety MCU that you can bring outside the SoC, but in your carrier board. We provide reference firmware. It is based on FreeRTOS today, but you can bring any safe RTOS of your choice and port it to FSI or SMCU, and we provide the OS abstraction layer for you to do that. It also includes some of these features like error propagation layer. So for you to pass on some of the monitoring and errors that are generated, custom errors from your monitoring your application, you can propagate those errors to FSI and safety MCU. To talk to the external world like motors, you need a safety protocol. We have Edge Safety Link as one of the safety protocol, but you can implement any other safety protocol like FSOE or ProfiSafe and such. So that's the hardware which is built with safety features, and then we, as I mentioned, we have the safety extension package software to enable some of the safety features. Along with the hardware and software, collaterals are also very important. So that's where we have a safety application node for IGX Thor, which tells how to address different standards on IGX Thor. It also has ongoing TÜV relevant certification at the platform level, and also it comes with safety manual, FMEDA, and such. Now, we talked about hardware, software, and the platform. I wanted to kind of give you a brief introduction into the two types of safety architectures that we're going to offer on this platform. For the simplicity's sake, I'm calling it as Safety Architecture 1 and Safety Architecture 2. In the Safety Architecture 1, which is on the left-hand side, so here we have CCPlex running a Linux OS. It can be an IGX OS, which is based on Ubuntu, or a Yocto-based OS. On top of that is the AI Enterprise stack. But what happens is the IGX OS or Yocto is where your AI perception is running because it has access to the GPU. Then is the SCP package, the safety extension package, which enables error reporting and other safety features on the IGX Thor platform. As I mentioned, there is an FSI, Functional Safety Island, which is built inside the SoC. We provide an FSI RTOS. Today, it is based on the pre-RTOS, but you're welcome. Our customers are welcome to bring any other safe RTOS of their choice. And we provide some reference code for Edge Safety Link. Then there is also Safety MCU. Again, the Safety MCU is the pre-RTOS is provided for Safety MCU. Again, even here, you can bring any safe RTOS of your choice. So now, if in this architecture, you have kind of two islands for safety. One is FSI and one is Safety MCU, while the CCPlex is running your AI workloads. In the Safety Architecture 2, the right-hand side remains the same, the FSI, Safety MCU, and Safety Extensions. The part which changes is actually the CCPlex. On the CCPlex, on the CPU complex, we run an NVIDIA hypervisor, and there we provide two VMs. One is a Linux VM based on Ubuntu or Yocto, and then a safe RTOS VM, which is QNX. So here you will have the AI running in the first VM, which is the Linux VM, because that's the only VM which has access to the AI workloads to the GPU. While the QNX VM has access to CCPlex and can run control loops or other safety functions. So in this architecture, you have three islands, if you may. One is FSI RTOS, but also FSI SMCU, but also on the CCPlex, you have the QNX VM. So there are two architectures. The first architecture is what we're going to provide as soon as we launch IGX beginning of next year in January. And the second safety architecture is going to be later part of the 2026 GA. Before I go to the outside, and I wanted to actually ask Bodo. Bodo, you have worked with us on assessing Orin platforms, and now you're working with us on Thor. Would you want to tell something about that?
Yeah, so I mean, the good news is that the two platforms are very similar, so that's helpful in the actual analysis for that. And then for both platforms, it's also critical to say that they've been used in automotive applications first, and so the platforms have been certified as for ISO 26262, which is the automotive safety standard. As I said initially, the upper level IEC 61548 safety standard is obviously the type A, and then the automotive is type B. So there are some differences, but there's also some similarities. And then we've been spending a lot of time basically identifying what similarities between the standards we can utilize, and then what type of safety work products can be reused in this case here. So, and then I mean, that's really, I would say, a large pillar of the work that's been done for the classical functional safety to make sure that we can build on that foundation that NVIDIA has been creating. And then when we are coming to the AI, then obviously now we have these new standards that we mentioned initially, and then that's something that we'll probably have to investigate more separately. But yeah, we are well equipped to do that.
Awesome. So now let's jump into the topic of outside and safety. So outside and safety is a new concept that we are bringing, which uses infrastructure sensors to in the context of safety. What do I mean by that is, instead of using, in addition to, of course, using the sensors which are connected to the robot for inside out safety, these robots typically are also commissioned inside infrastructure like warehouses or manufacturing plants. They have sensors like cameras on the ceilings or on the walls. Using that to perceive the world from a different angle, in lack of better terms, it's like God's eye point of view, and looking at human-robot interaction, robot-robot interaction, and looking at safety situations, and kind of expanding the perception capability of the robot. Now, not only it can see through its own sensors, but also the sensors which are connected to this to the infrastructure. So that's what is outside in safety. Of course, as I mentioned, one of the challenges that we said about traditional safety not being able to provide 360-degree situational awareness, outside in safety kind of plugs that gap by providing a 360-degree situational awareness all the time, because it does not deal with blind spots or any occlusions. So how it works is there's a perception safety perception AI which perceives the safety situations which are happening, and there are multiple models built into it. So there are multiple models looking at the situation and looking at safety situation. For example, a person coming close to a robot. Then there is a safety monitor. The safety monitor is monitoring not only the correctness of the events generated by the AI model, the perception of the AI model, that not only detects the correctness, but also the monitors the safety, the sensor data, whether the sensor data is coming on fine. Along with that, there is also a vision language model, which is seeing through the scenario, seeing through the video feeds, and understanding the video feeds and doing something like safety auditing in parallel. So once you perceive a safety situation, once the monitor detects that yes, the safety situation is actually valid, then the outside in safety through black channel can communicate the safety situation to the robot, the inside out mechanism which is built inside the robot, to take further actions, which could be slowing down the robot, stopping the robot, or anything like that. So this particular concept is inspected by TÜV Rheinland for SIL2 performance level D capability. And also we're looking at now the application user level A1. I want to show you a quick demo. This demo is actually coming from a use case which is in logistics, which is a trailer loading use case. Here there is a trailer which are these two doors. You can think of it like a trailer which is backed up to a warehouse, and there's an autonomous forklift which goes ahead and then loads this trailer. One of the main problems of that with the traditional safety mechanism is that once the autonomous forklift enters the trailer, for it everything looks like a safety situation. The walls of the trailer, the other pallets look like safety situation. It constantly stops, and that's where the performance of the robot goes down. Now, what we have done with outside in safety is through the infrastructure sensors. If we find that there is no one in the vicinity, there's no human in the vicinity, then as soon as it enters the autonomous forklift enters the trailer, we mute the safety functions, and that's why they can do its work inside the trailer more efficiently. I'll show you another scenario where you'll see that now there are people in the vicinity, and hence you cannot mute the safety functions because there are people around it, and hence it will keep the safety, the normal safety functions until all the humans exit out of that safety zone. So this not only makes the robot safer, but also more performant and increases the productivity of the forklift. In parallel, we are doing a safety auditing through a vision language model, which is running in parallel. So IGX gives the capability to have an iGPU and a discrete GPU. So this the left part, the safety part, is running on iGPU, and then the vision language model for safety auditing is running on the DGPU, and completely separately. So very quickly, Riccardo, you want to go over the architecture?
Yes, absolutely. And I was also reading the question. Wow, very, very interesting. I'm really amazed. So let's say in essence, the architecture is the following one. Let's start from the left side. You have a set of cameras and other sensors that may be connected as well. And one point was, what about if one sensor is failing or if, for example, one camera is occluded, and this is why you typically need a redundancy, so different set of cameras at different angles, so that you can cover both the failure of a camera and the issues on the respective, let's say, side of the view. Then this information is fed to the platform at a very low latency. And again, there was a question that, and it was really on spot. So when you want to use a system like that for safety, you need to have a very low latency. Now, how much, let's say, how low the latency is depends also on what you need to do, on the size of the region of interest, on the position of the tripwire. But so definitely you need to have a latency that is very, very small, in the order of 100 of a millisecond or much lower, in order to get to that objective. So all of that is inputted into a pipeline where you have your models. And the models, they depend on the task. So detecting humans and detecting forklift, detecting AGV, and then those models generate a set of events. And then we have a safety event integrator. Integrator means that you collect all these events, you sort them in terms of when they happened, you synchronize those events, and then you create a scenario. It's basically a fusion. And this will be, by the way, also the place in which you have, when you have not just camera but other sensor, you do a sensor fusion. And then at the end, you send that to an element that take a decision. This one strongly depends on the use case. So in this case, is deciding if you unmute or you mute the safety function operated into the external forklift. And then you dispatch that information to an end-to-end safety protocol, for example, in this use case, wirelessly to the inside-out safety. So that is the overall flow. However, this is safety. So basically, it is essential that we monitor all what's happening, and this is why we have a safety AI monitor. So the role of a safety AI monitor is, in essence, to implement, if you remember one of my first slides, the guardrails for AI. So this is the runtime type of guardrail, in which you have detection of, for example, out of distribution detection, or out of your the design domain. You also need to evaluate the uncertainty of the output. So, and I think has been shown earlier on by Bodo, there is one standard, the TS 25223, that is now in construction, in the same working group of the TS 22440, that is exactly about how you quantify and evaluate uncertainty. And so such as, and other things, including embeddings into the model. So the safety I monitor basically is deciding if what's happening is trustable, is reliable for having a decision for safety. Otherwise, the system is not operational. Then the other element that we need for safety, of course, is a safety event logger, in which you store all what's happening, the event that is happening, as also any near misses that can be used when you do your offsite, offline analysis.
So, Bodo, you worked with us on safety assessing this architecture and this concept. Do you want to talk about that one? And
yeah, I'll give you guys a quick overview, and I think we had some questions in the chat about this anyway. I mean, what does safety assessment really mean? And I'll go through the points in the right first. I mean, so usually you have an accredited entity like TÜV Rheinland going in there and inspecting something, and then in the end there's a report that's coming out of that. That report is going to be accepted by other accredited entities as well. So I mean, so that's why you saw on Riccardo's slide, maybe one entity is doing a certification for automotive for something, and then the other takes the results over, and then can use these results to then work on industrial safety or something like that. And why are we doing this? Well, I mean, so 150 years ago, the world was probably as exciting as it is today. Things, although were probably exploding quite a lot, at least in Germany. You know, so you had all these steam boilers during the Industrial Revolution, and these steam boilers tended to explode, and people were getting hurt or killed. And obviously, that was something that needed to be prevented. And then here in the US, some of you people might have heard this in school. Chicago, the big fire. So fire was a big hazard in the US, and then both of explosions and fires led to the need for entities that go in there and then basically check out structures, buildings, systems to make sure that they don't explode or catch on fire. And obviously now there are additional hazards, but that's basically where companies like TÜV, UL, and others were founded. And then, so now when you're doing this, then we've been doing this for 150 years. A lot of these techniques and methods that we're using are pretty traditional. So you've heard of maybe a failure mode and effect analysis, fault tree analysis, HAZOPs, and so on. A lot of that stuff goes back to World War II, and it's been used ever since. These are useful techniques, and every inspection body that you can find nowadays really knows how to use them well. They also know how to look at them in a good way. And if people are making mistakes, we usually catch that. So that's a good thing. However, if you have something new like artificial intelligence, machine learning, and if that's not defined in best practices or standards, then, well, things are getting more interesting. So that's the scenario that we're in right now. And it also needs to be said that standards and accreditation take a lot of time. New concepts take a lot of time to get established. So bottom line, this is my takeaway that you should take from this slide. It's difficult to get AI and ML safety certified currently, another 10, 15 years, and the situation is going to get better. If you do want to do this though, then actually, hang on, if you could go back real quick to the last slide. Just a high level, I won't bore you with all the details, but usually what we do is we have a three-step process. So we basically, first of all, talk about what type of scope people want to get stuff certified in that defines the standards that you want to use and so on. And then we go through what we call a concept phase. At that phase, you're basically putting your things together. It's not super mature at this point yet. So I mean, we wouldn't expect hardware or software design artifacts, and probably not all the system artifacts as well. But then in the main assessment, we would go through all the nitty-gritty stuff. I mean, so at that point, you have to have everything available for your design artifacts. We'll go through and then make sure that whatever safety mechanisms you put in actually are satisfactory and are likely to work. And then in the end, if this all passes, you'll get a report. So that's that. And then now if you could go to the next slide real quick, we'll show you how this is actually being done in the example of an industrial perception subsystem that's using AI. So the Halos system here. So you can see in the top left block, the standards that we were using. Then you can see that we needed to define safety relevant functions and their safety levels. Then you guys already stole my thunder, so you already know what type of AI system requirement and classification we have. And then we also need to look at the environmental conditions that the system will be used in. Tool confidence is a point. And then even at the concept level, we like to see some sort of a system FMEA or system FTA, and then fault detection and control method that's been utilized. And then in this case here, NVIDIA has been doing a great job in putting the methods, techniques, and KPIs together that are going to be used in the main phase. And so all of this basically gives us a good foundation to then go into the main assessment here. But in the right, you basically see the takeaway that I have here. So for the concept review, we need each of these blocks on the left. We need evidence for that. So you got to provide something, documents or whatever that can be used as evidence. Sounds like a court of law, and a little bit it is. And if it comes to something bad, stuff like this might actually end up being used in a court of law. So that's why we are really careful, making sure that this is consistent and concise. And then we basically go through the main artifacts and comment them. And then in the end, if you have supporting artifacts here, then we usually do sample checks for these. We wouldn't go through everything here. But yeah, so that's that. And then so basically, so in the background here, you'll see the concept report that we are going to be issuing here very soon for the Häuser outside in project here. And then if you slide forward, then we'll get the so these are the two key safety functions that we have for the project. And so the one is obviously to detect and infer and localize humans and forklifts. We talked about that. So the target is going to be a SIL2 or PLD, a category 3. Oh, no worries. I mean, so luckily I have a backup here. So, and then the second safety function is this safe to mute function we talked about. I mean, so we need to communicate to the autonomous robot that we have, that forklift, whether it's safe to disable the mute, the person detection function or not. So this safe to mute signal, that's the other high level safety function that needs to be sent. Yeah, and if you want to advance one more, I mean, I won't go through the whole list here, but I mean, this is basically part of the inspection plan, and then the document that NVIDIA is going to get out of this. Each of these bullet points here is going to yield a section in the document where we look at sufficient evidence for these things. So I'll pick one, functional safety management, for example. This is really the probably least sexy part of this whole thing here, you know. So it's basically making sure that the plans are met, that everything that you said you would do, you are doing throughout the project. At the right time, it's being planned. We talked about tool confidence. So, I mean, we basically look at that's being happening. So, and then if you want to advance one more time, then, and sorry, this is a lot of text and you don't have to read through this, but in the end, I mean, it's going to be basically saying that, hey, the things that we set out to do here look feasible. So, I mean, so we'll basically get an ALU A1 system here that, and for us, the classification for that made sense. Obviously, it's this one wouldn't be one hard to agree with because it's the most stringent category anyway. Then it's a systematic capability, AI systematic capability of 2, which really maps nicely to the IEC 61548 systematic capability of 2 that we already talked about. And then in the end, we'll definitely say, hey, I mean, so this is going to be useful in a SIL2 hardware fault tolerance 1 and PLD category 3 environment. So that's what we need for this this scenario here, because the hazards that we are getting here basically justify the SIL2 classification. And yeah, and so in summary, so that's basically what this report's going to say. And then so now we've took the first hurdle for this, so we have a solid concept for this, but then now in the main assessment, we'll have to make sure that we can actually show the actual hardware, software, and system design artifacts and the verification and validation artifacts to prove that that's all good. And if we do, then then we'll have a system that can be sold and used according to these criteria.
Thanks, Bodo. Very quickly, I think since we're almost out of the time, so this is how we're going to release the Halos outside in. We want to release it as a blueprint so that anybody can then develop on top of that. That blueprint will include AI models, the ones that we are using. We pre-trained models for safety perception. Today, for example, in this particular use case, it detects person and forklift, but it can be trained for other object classes as well. So we'll provide the fine-tuning tools for that. And these models are optimized also for latency. As Riccardo was mentioning, latency is extremely important from when the actual safety situation happens to when the actuation happens on the robot. So we have a goal of end-to-end latency of, depends upon the use case, but under 400 to 500 milliseconds. Then for the model that has been used, the safety card, I would say, it includes data quality, what type of quality of data that was used to provide, train the models, test quality, AI failure modes, and that kind of collaterals will be provided. Again, safety concept report, which is already SIL2 performance level D. And this particular architecture supports multiple sensors, as we already saw, and also but multiple modalities. You can expand this to bring other modalities as well. As I mentioned, this is we would have done it for one particular use case, but then if you want to adapt it to a different use case, you would need to, for example, fine-tune your AI model. We'll provide tools for that. For plugging your, augmenting your data quality and test quality metrics and reports, we will have other tools like synthetic data generation for creating those training data to plug your gaps. We'll provide the calibration tools for sensors and also camera placement guide, for example. Where do you place the camera for the maximum accuracy and performance? I'm not going to go through this 2 slides because since we ran out of time, but it was almost like how do we expect people to go to deploy this? With that, I'm going to stop sharing and see whether Edmund, do we still have time to take a few questions?
We absolutely have some time. If nobody has a hard stop, we definitely have a bunch of questions. Now, some of these questions I think are a little deeper and would be better for the Discord server where we can engage afterwards. But what I'm going to propose is we've had our great producer Amelia with Rick go over some of these questions and they start some of the ones they thought would be good for us to touch on. What I'm going to suggest, some of these questions will be hard to do this, but I know we have some great, brilliant minds here on the panel. So I'm going to suggest that you do your best to try to do lightning answers on some of these. So just really, really high level answers on some of this. We can cover as many as possible and just direct people to Discord for further discussion on that topic. How does that sound?
Yeah, no, I think sounds great. And maybe I can start. I see Sanjana. I hope I pronounce her name right on LinkedIn. It's a great question. How does the safety AI monitor determine when the perception uncertainty is high enough to deactivate the system, and what metric or threshold do you use for that decision? Yeah, it may take an hour just to answer that, but I want to pass an important message, is that first you stop a target in terms of the, let's say, what is the acceptable rate of failure of the system. And then we're starting with that, then you define the KPI, and then per each individual monitor, then you identify the threshold. So it's not just a magic number that we put starting from bottom, but it's rather a top-down flow starting from the top level argument down to. And then this is where you get such a numbers. But
Amazing.
yeah, we will give more detail on Discord.
Okay, cool. And good segue. I don't know if you predicted I was going to put that on the screen, but we got a question asking, how do I get the Discord? So we'll put the Discord address in the chat so everybody can get to it. It's pretty easy to remember. Discord.gg/NVIDIA Omniverse. We'll put the invite link in there. And Amelia has already created a thread under our Discord, our live streams category for this specific live stream. We're also going to put the deck there. That deck was one of the most informative decks I've ever seen in terms of information presented. So there's a lot of good info there. We'll try to put that deck in that Discord thread as well. Okay, so do you guys want to pick from the stored column here, and I'll try to put them on the screen? Or do you want me to go through and pick some of these questions from the stored column?
Yeah, so maybe I can take one and might also ask Bodo to help. There is 2 questions from Jack Cotta. Let me. So basically, is the relationship with the ISO 42001? So I think that is a valid topic. So such a ISO standard is overall about the AI aspect, is not just for safety in general. So what we provide and what we deliver is what we call an AI safety manual and safety and also a safety card of the models. And then we combine all those arguments with other elements. And so it may be within a framework like the ISO 42001. So that is the overarching thing.
Okay, well, thank you for doing that.
We'll pick one from sensor data. Any failover logic, if one Halo sensor drops, does the system still keep the safe zone? Riccardo, you want to take that?
Yeah, so I think I said it earlier. So there is some redundancy. Now, redundancy is never something you put, let's say, like somehow random. Is related to the failure mode. So, for example, if there is a failure in one of the camera, then you have some redundant camera. Then, if there is a failure of the hardware, as we have shown, you have basically 3 islands that can take some actions. So so the short answer is we have redundancies and we connect to the failure mode analysis. And depending on that, it could be software redundancy, hardware redundancy, model redundancy, or sensor redundancy, and also different sensor modality.
Thank you. That's great. Okay, cool. Let's go through some more here. Do you guys see something you want to take? We're going to pick one up. And thank you, everybody watching, for submitting and comments throughout the live stream. It was very helpful to see the feedback in real time.
Yeah, I think another one is I think it was related to more general if those architecture are Halos. So Halos is really everything, and you can take all or any of those layers. So the platform that has been shown, IGX, the safety of IGX is infused by Halos. The outside in safety agent, we have the AI safety monitor is where we have Halos. So Halos is basically every layer of the technology and the safety of it.
Yeah. So Riccardo, there is I have probably a question from my side that I forgot to get your thoughts on. Is the same AI safety architecture that we showed for outside and safety can be employed in inside out manner as well to bring AI in an inside out manner? Can you comment on that?
Yeah, no, absolutely. I think the architecture we have seen, and in particular the basic structure of the safety monitor, the safety decision maker, the safety integrator, those will be valid still for inside out. And also the whole process. I mean, we have not went into the detail of it, but as shown by Bodo, one critical point is how you identify the failure mode, the data sets, so how you generate data set for training, for validation, testing. So somehow all the end-to-end, I would say, flywheel for data. So I would say all those elements are certainly applicable to inside out. The model may be similar, may be different. Of course, the way you integrate sensor may be different, but the architecture for AI safety will be the same.
Great question. Let me see. So we have a couple other ones here. I don't know if we actually covered a really basic overview here. Someone tuned in at the middle and was asking, can we define outside in, inside out? For maybe those who are kind of new to this topic and are thinking about the Pixar movie, perhaps. So do you guys want to define this, everybody?
Yeah, I can take. We define inside out is when the robot is using the sensors which is connected to it and looking at the world in an egocentric point of view. So from its point of view, that's inside out. And outside in is where you are looking at the same robot from a different perspective, from a God's eye view, using the sensors and the infrastructure, and looking at a robot interaction, robot-human interaction. So you're looking at it from a different angle. So you are looking at it from an outside-in view. So that is the distinction between inside out and outside in.
Okay, that's great.
Yeah.
I see a question here from Grand Prix News on YouTube. This user is asking, for the Isaac Sim integration, can Halo stream its data as ground truth labels in real time, or is it limited to an offline pipeline?
If I'm not wrong, I believe the question probably could be related to the hardware in loop. But what you can do is actually simulate. What we showed was actually simulation. So you can simulate everything on the Isaac Sim, but that simulated Isaac Sim data is then pushed on to the IGX, which is actually the where the perception and the other workload is going to happen, and the results goes back to the Isaac Sim. So that is how we also test it. So yes, Isaac Sim integration can happen in hardware and loop manner as well.
Okay, great. Let me see. Here's another question from YouTube. So in outside in, the item definition is the entire environment where a robot would be situational. Just confirming that.
Maybe I can take that one. I mean, so this is industrial safety. So an item definition is really an automotive term, and in automotive, item definition says, hey, I mean, this is basically you draw a box around the function that you're trying to do. So maybe an adaptive cruise control or something like that. So so if I believe what the person asking here is, I mean, this is more like the operational design domain for the system. And the way we interpreted that when we looked at the ODD description was part of the inspection that we've done, that then any time or any type of operation that's been defined in the overall system description was part of the ODD. And if there are certain things that you want to add, so like, for example, in this case here, the systems plan to be used inside a building. So if you wanted to change that and then maybe the fork truck operates on the outside, then that wouldn't be valid anymore. And now the ODD would have to be changed, because now you'll have things like rain, maybe snow or something like that affecting the system while inside the building. I guess the most slippery thing I've seen in the ODD description was a potential oil spill or something like that. So hopefully that answers that question.
Very helpful. Thank you. We'll try to take a few more here.
There is the one about the VLM audited agent, and I think it's important. So and it's the right question. So every time we build something for the great use of AI, and then we bring back into the safety, of course, we need to apply somehow the same things you have seen for the overall outside in safety architecture. So what does it mean? Is that the reasoning VLM has to be analyzed with respect to the ISO ICTS 22440 in this case. And so it will start about the role. So in the TS 22440, we have different application user level. If the AI technology is used to directly generate an outcome like the one we have seen, or if it uses a diagnostic, or if it uses an online tool or offline tool. So assuming in this case we use the VLM as an offline tool, basically to review offline during either the validation or when we analyze the near misses, then there is an Annex C in the TS 2440 that is somehow describing the requirement that include the way you analyze the failure mode of the VLM in that context, the verification and validation you need to do, and of course it will be back to the principle of AI safety. So how you demonstrate that the properties like transparency, explainability, and so forth are reached. So that was a great question as well.
Well, thank you for addressing that too. And I have to say, Suhas had to drop, so he wanted to say goodbye. He chatted with me offline here. So he thanked everybody for jumping on live stream, guests and viewers included. Okay, so that's a great. Do you guys have a few more minutes to try to tackle a couple more of these questions? Maybe one more. Maybe one more.
One more.
No,
but it's really a good question. Yeah.
All right, go ahead. I want you to pick it since this is the last one.
So I think maybe we can very quickly discuss with Bodo what standard, I think there is no name, what standard framework are there for FMEA for ML-based approach?
Yeah, thanks.
Yeah. Bodo,
yeah, that was going to be the one that I would have wanted to talk about. Right. I mean, so
okay, go ahead.
So currently there really isn't anything, but coincidentally, former colleague of mine and Riccardo, I actually sent you an email about this, started something. We actually had a paper in let's see, it was an SAE paper at the beginning of this year that was titled the use of FMEA for machine-based learning. That one was developed together with Talk Robotics, but now we actually have we started a little working group, and then the question really is whether we push this into either a standard organization if they want to take this off, or maybe do this on their own. But what I can do is if you either Google that, then you can see that. I mean, there's a GitHub framework where you can download some of the documents that we've been preparing for that basically show you how to actually do a process FMEA for a machine learning pipeline for, in this case, an autonomous vehicle. And it also has some of the failure modes preloaded for this. So that's basically the extent of what we have besides what's mentioned in the standard documents. But yeah, I mean, there seems to be, I've been always belittling this because I said, hey, in FMEA, this is an 80-year-old technology, but looks like there's lots of people interested in that. And then the really good question about this is, what are the failure modes? And so like I said, there's some stuff available that you can get download from GitHub, and then you can also get the SAE article. And then there's a couple more coming out that we're working on right now.
Amazing. As we close out today's stream, I want to remind everybody that GTC San Jose is in full swing in terms of planning. You can get notified for updates by clicking that notify me button. Just go to nvidia.com/GTC, especially if these kind of conversations and this kind of information is compelling and helpful, and the networking. Imagine being able to meet folks like Riccardo and Bodo here. GTC is an amazing place to do it. Highly encourage everybody to come. We have another live stream that's starting in 45 minutes, I believe, if you're watching live right now. So I highly recommend those who are interested in building digital twins of physical AI, jump in. Same NVIDIA Omniverse channel. We're going to cover this, including Brev as part of that. Super exciting. Riccardo and Bodo, I can't thank you enough. And of course, Suhas earlier. What an amazing presentation you have all put together. Really honored to be working with my colleagues here, but also really honored that and humbled that, Bodo, you were able to join us today. It's very clear that your expertise in this area is really impactful, and I could tell it helped a lot of people in the audience. Speaking of which, thank you to everyone in the audience. Really great questions.
Yeah, really great questions.
We don't want to forget those. So listen, for people who haven't used Discord, it's not that hard. If you've used any kind of messaging, it's really easy. So just go to the Discord server. Amelia's already created a chat. Message me if you need help on LinkedIn. I'm happy to share my screen and walk you through how to use Discord. We will post information, including the deck there, and you can post any questions that we didn't get to cover. If it really is needed for your work, please repost your question on Discord. I promise I will bother Riccardo and Bodo and Suhas to go on the Discord server and answer them for you. But go ahead and take that next step and post your questions there. I'm sorry we didn't get to cover all of them, but thank you so much for watching today. It's been a real honor to be with everybody today. Thank you, Riccardo and Bodo.
Yeah, thank
Thanks,
you.
guys.
Thank you, everyone.
Thanks for having me.